Hi, everyone. Welcome to chapter 12. In this section, we are going to look at one-way ANOVA. And the way that we are going to be tackling this one-way ANOVA is using technology. We can use StatCrunch or we can use StatDisk. In this section, we introduce the method of one-way analysis of variance, which is used for hypothesis test of 3 or more populations that have means that are all equal. That means that our null hypotheses will be that mu1 is equal to mu2 is equal to mu3. That since the calculations are more complicated, the results. We are going to be looking at an F distribution. So an F distribution is going to be a pair of degrees of freedom for each numerator and denominator. So there's a value of F, the standard deviation of the numerator over the standard deviation of the denominator, S1 squared, the variance, S1 squared and S2 squared. Remember that the F distribution is not symmetric, is actually skewed to the right. The values of F cannot be negative. And this is also a right-tailed test. We'll start with a one-way analysis of variance that is also called ANOVA. ANOVA is the method of testing equalities of 3 or more population means by analyzing sample variances. One-way analysis of variance is used to treat categorized data for one factor or treatment. So there's one characteristic used to separate the sample data into different categories. We'll start by using the samples from 3 or more different populations to test a claim that the populations have all the same mean. So what we're going to be given is a minimum of 3 data sets. The populations have to be distributions that are approximately normal. The populations have the same variance, sigma squared, or the standard deviation. The samples are simple random samples of quantitative data. The samples are independent of each other, and the different samples are from populations that are categorized in one single way. So to evaluate this, we're going to be using technology to obtain results that include a test statistic that's going to be the F test statistic and the p-value. We are going to be identifying p-value from the display of the ANOVA is a right-tailed test because only large values of a test statistic cause us to reject the equality of population mean. So again, we are going to be using StatDisk or StatCrunch to solve and look at the p-values and the test statistic. We are going to be forming a conclusion based on the criteria that we've done in the past. If the p-value is less than or equal to alpha, we are going to reject the null that all of the means are equal. We are going to fail to reject. If the p-value is greater than alpha, we are going to fail to reject the null, meaning that the hypothesis is equality. We are going to be using technology. So understanding that if a p-value is small, then we are going to lead the rejection of the null hypotheses. That would mean that with large values of p, we are going to fail to reject. We are going to be developing a understanding and underlying a rationale by studying the examples in this section. Let's begin by looking at example number 1. Example number 1, lead and performing IQ scores. Use the performance IQ scores listed and a significance level alpha of 0.05 to test the claim that 3 samples from a population with means are all equal. So the hypothesis is the equality that mu1 is equal to mu2 is equal to mu3. So we have in this example 3 different datas. So this is population 1, population 2, and population 3. So we already know that we are going to have at least 3 samples. So at least 3 samples. So we are going to use ANOVA. Our null hypotheses will say, well, mu1 is equal to mu2 was equal to mu3. And the alternative is that at least one is different. So we need to see if we can use the ANOVA. So the ANOVA is the requirements. They must be an approximately normal. So if we look at the data from each of them, they do show approximately normal. And they're simple random samples. They're from quantitative data. So all of the requirements suffice. So in order for us to actually perform the ANOVA test, we are going to go to StatDisk and we're going to look at the p-value. So let's do that together. I'm going to go into my computer and then I'm going to share my screen from StatDisk. So I'm going to go into StatDisk. And notice that I've inputted already. So this row here represents all of the values from the low blood level. So 85, 90, 107, I have to list all of those values already here. Notice that they're already included. So this is from slide 11. The data from slide 11 is right here. So slide 11 from section 11.1 is exactly all of this data. You have to input all of the data. Then you're going to go to slide 12. You're going to put in the median blood level on the next one. So 78, 97, 107, 80, list them all out. And then the third population is a high blood level. So 93, 100, 97, 79. Again, all this data is coming from my slide 12, my third population. Now that I have them all together, they are all independent. We are going to make sure that we look at the alternative hypotheses and the null hypotheses. So I'm going to share here my iPad. There's my null hypotheses. There's my alternative hypotheses. Now I'm going to go to StatDisk because I want to be able to identify the p-value. Remember that we are going to reject the null if the p-value is less than or equal to alpha, and you're going to fail to reject if p is greater than alpha. So let's go into StatDisk. Now that I've inputted all of my data values, you see here, my data 1, my data 2, my data 3, population 1, population 2, population 3. You're going to go into analysis. You're going to go into one-way analysis of variance, that is ANOVA, and you're going to tell it what columns to include in the analysis. I want you to include data 1, data 2, and data 3. That means population 1, population 2, and population 3. I'm going to select evaluate, and I'm only going to be looking here. I know that there's a treatment, the error, don't look at that. We are going to be talking about that. We are going to look at the critical value, the test value, but most importantly, the p-value. So the p-value is p is equal to 0.01951, which is less than or equal to alpha. That interpretation already tells me that since the p-value is less than alpha, we are going to reject the null because the p-value is low. We also look at the critical F value and this test statistic. If we select, if we select the plots, look at the critical and look at the test statistic. It's inside. We have a right tail test. It's inside. That also proves that we are going to reject the null. So if we look at both of these studies, we can conclude that the p-value is less than the significance level. We will reject the null. So when we reject the null, we do have enough evidence to warrant rejection of the claim that the 3 samples come from the populations means that are all equal. So using the sample of measurements listed, we conclude that those values from those populations have means that they're not all the same. So since we reject the null, we support the alternative. So since we reject the null, we support the claim of the alternative hypotheses. that not all, at least one is different, at least one mean. Okay, so that would be our interpretation. So on the basis of ANOVA test, we cannot conclude that any particular mean is different from the others, but we can informally note that the sample mean for the low blood is higher than the mean. It appears that the greater the blood levels are associated with lower performance of IQ scores. So what is the caution? When we conclude that there is sufficient evidence to reject the claim, we cannot conclude from ANOVA that any particular mean is different from the other. So even though we support the claim of the population means, the ANOVA doesn't tell us anything about the particular mean is different from the other. We can't identify which one it is. So how is the p-value related to the test statistic? So larger values of a test statistic result in a smaller p-value. So if you have a large value of an F, your smaller p-value it will be. So look at the values here. If the sample means are all closed, then we are going to fail to reject. That means that your F statistic is on the left side. If you have a large value, then you have a small p-value right here. That means that your F is large and you are shaded to the left area. We will reject equality. So one, we will fail to reject equality. The other one, we will reject equality. That will be the relationship between the F test and the p-value. So it depends on where you are. So if you have a large F, you have a small p. If you have a small F, you have a large p. Now, the test statistic for a one-way analysis, the test statistic for one-way analysis is the division between the variance between the samples and variances within the samples. So there's a difference between and within. So the numerator of the F statistic measures the variation between the sample means. So this will be the numerator over the denominator. The estimate of the variance in the denominator depends only on the sample variances and is not affected by the differences among the sample means. Consequently, the sample means that are close in value to each other result in a small f and a large p. So we talked about that. When you have a small f and a large p, we will fail to reject. Now, to calculate the test statistic of F with equal sample sizes N, the table on the next slide can be very helpful in understanding the methods of ANOVA. In the table, compare data sets A. We're going to be comparing data sets A with data sets B, and see that the data sets A and is the same as data set B, with this notable exception. The sample size 1 differ by 10 if the data sets have the same sample size as n equal 4 from the table. The calculations are not too difficult. So instead of having to do this using technology, we can do this by hand. We're calculating this by hand if the sample size is reasonable. So right now we are going to look at the table. We are separating data set A, data set B. Looking at the sample. So sample 1, sample 2, sample 3. We are going to look at each of the individual columns. We are going to look at N1 has 4 inputs. We find the sample mean, the sample mean for the first data, 5.5 and the standard deviation for this data. Sample 2, it has also 4 values. The sample mean for the second sample is 6 and the sample the sample variance is 2. Now, sample 3, so we look at them independently. 1, 2, 3, 4, that corresponds to 4 values. We look at the mean, so add and divide by 4, we're going to get 6. And we calculate the variance of the third sample, which is 2. Then we look at the other data, data set B. Data set B also has 4 values Now this has a sample mean of 15.5 and a sample variance of 3, so on and so forth. So we're looking at them independently. So if we look at step 1, if we look at the variances, we're going to use the formula of n times the sample standard deviation squared for all of the data. So we know n is 4. And then we look at all of the variances of all of the data that results in 0.0833. We are not going to require you to do this by hand. This is just showing you how data set A and data set B are going to be calculated if you would do this by hand. We are not going to do this by hand. This is just showing you that the calculations are simpler when you have a smaller sample size. To find the critical value of F is found by assuming a right-tailed test because of large values of F corresponds to significant differences among means, with K samples each having N values. The number of degrees of freedom are as follows. We are going to use K to be the number of samples and N the sample size. So how many samples we have versus what is the sample size of each sample? We are going to have a numerator with the degrees of freedom of K minus 1. The denominators will have degrees of freedom of K times N minus 1. Remember, we are going to be using StatDisk and StatCrunch to solve. We are not going to do this by hand ever. So don't worry about the formulas. We are not going to need them. So how do we understand the effect of a mean of the F-test statistic? To really understand the method of analysis of variance, consider data A and data set B in the recent table to take note. The 3 samples in data set A are identical to the 3 samples in data set B, except for each value in sample 1, the data set B is 10 more than the corresponding value. So instead of 7, we have 17, 3, 13, 6, 16, 6, 16. Do you identify that? So just on that first sample is what it changes. So adding 10 to each data value from the first sample, it has a significant effect on the test statistic, with F changing from 0.1428 to 5157. Adding 10 to each data value also changes on the p-value, 0.86 to 0.00018. Looking at the p-value. So just adding 10, the number 10 to the first column, so 7, 17, 3, 13, it's going to change significantly my p-value and my F value. That's what this is saying. So the 3 sample means in data set A are very close, but the sample means in data set B are not that close. And that's because of the 15.5. The 3 sample variances in data set A are identical to those in data set B. In data set A is 0.332, but on data set B is 120, indicating that the sample means are farther apart. So looking at the data that we're given, so we have the sample variances, 0.1333 and 120. And that is because just adding that 10 dramatically changes the value. So the variance within samples is 2.33 in both data. Because the variances within sample isn't affected when we add a constant, the change in the F-test statistic and the p-value is only attributed to the change of the mean. So this illustrates the key point underlying the method of ANOVA. And this is the key point. The F-test statistic is very sensitive to sample means, even though it's obtained through 2 different estimates of a common population variance. So F statistic is very sensitive to sample means. So if it's highly sensitive, we remember that anything that is highly sensitive, we have to be very careful if we add or subtract any particular values. In this case, we added 10 that dramatically changed our p-value and our f-test statistic. So one way to reduce the effect of extraneous factors is to design the experiment so it has a completely randomized design in which each value is given the same chance of belonging to different factor groups. Another way to reduce the effect of extraneous factor is to use a rigorously controlled design. So there's two ways to reduce the effect of extraneous factors: randomized design and a controlled design, in which sample values are carefully chosen so that other factors do not have any variability. So what does this mean? After conducting an analysis of variance tests, we might conclude that there is sufficient evidence to reject a claim, but we cannot conclude from ANOVA that any particular means are different from another. Here are two informal methods for comparing means. We can construct a box plot of different sample values to examine the overlap, or we can construct a confidence interval that estimates the means from each other from different samples, and then compare those of those confidence intervals to see if one or more of them do not overlap. So which are the formal methods? The way that we're going to do, there are several formal procedures for identifying which means are different, and those are called the range test. The range test allows us to identify the subsets of means that are not significantly different from the others, or we can do a multiple comparison test, which uses the pair of means, but we need to make adjustments to overcome the problem of having significance level that increases as the number of individual tests increases. And there exists this test called the Bonferroni multiple comparison test. So we look at step 1. So we do a separate t-test for those each pair of values to make the adjustment described. We are going to look at this t-test. Do not worry about this t-test or this MS error. This MS error is also calculated on StatDisk or StatCrunch. That's given. And what this does, it allows us to use all of the available sample data. So after calculating the value of the test statistic and looking at the t-value or the p-value, we use the degrees of freedom of n minus k, where n is the total number of sample values, and we look at the critical values. If we look at the first example, we conclude that there is sufficient evidence to warrant rejection of the claim. We want to use Bonferroni's test with an 0.05 significance level to identify which mean is different from the others. So we are going to let the null hypotheses separate mu1 equal mu2, mu1 equal mu3, mu2 equal mu3. So here are the null hypotheses to be tested. So then we can identify which of the means is the different one. So what we're going to do is we're going to begin with the null hypotheses of mu1 is equal to mu2. Using the sample data, we're going to carry the decimal place. So what we're going to do is we're going to go back to StatDisk, and we are going to look at the different errors. There's this MS 248. We find the p-value. We see the sample standard deviation of each. So we notice that the MS error is 248.42. That's the value that we obtained from the first example. So then we could evaluate what is the mean from the first data minus the mean of the second data. We can easily do that if we look at, move over here, and this is our sample editor. There's our values. I can ask, okay, find, if I copy and paste the data, and if I want to find the mean of the first, the mean of the second individually, we can solve finding the t-value. So remember, when we looked at the results of the t, here is the t was not given. We can evaluate the t by finding the value. So there was this MS error. We found, there's our sample editor. We can copy and paste this data and find what is the mean of this data. X1 bar, that's 102.705. We can find the sample mean of the second population individually. We can copy and paste this column and find the mean of this column. The value of the value of N1 and N2. So what's the value of N1? There's 78 total values. How many N2? There's 22. We could plug this in our calculator to obtain 2.252. Then we're going to look at the degrees of freedom, which is the total value of N. N is the sum between N1 plus N2. So 78 plus 22. 121 minus 3. There's 3 degrees. Our K is 3 because there's 3 populations. So we get 118. There's our test statistic. There's our degrees of freedom. And there's our p-value. So then again, we already know that the p-value, if the p-value is small, then we have a large f value. So that means that because the p-value, it's not small, the p-value is less than 0.05, we will fail to reject the null. So it appears that the sample 1 and 2 do not have significantly different means. So instead of continuing with separating hypotheses test, we will use the SPSS display to show all of the Bonferroni tests. So this will be given to you. So what we're going to look at is the differences between the standard error and the significance level and the mean difference. So this is given. In these results, low levels are represented by 1. There it is. The median level are represented by 2, and the high level are represented by 3. When we look at the data, although the analysis of variance tell us that at least one of them is different, the Bonferroni tests do not identify any particular sample mean that it's significantly different from the others. So let's look at the sample means. Look over here. Look at the differences here. Okay. So the Bonferroni test, what allows us to do is to actually look at the mean difference. Is there a lot of differences between one or the other? Are they significantly different from the other? And that finishes section 12.1. In 12.2 is an extension of 12.1. And now it's just called the two-way ANOVA. Again, the two-way ANOVA can be evaluated using StatDisk or StatCrunch. This section describes the method of a two-way analysis of variance, which use the data partitioned in according to 2 factors. The method of this section requires that we first test for interaction between the 2 factors. So we're going to see if they're independent or not. Then we will test for an effect of a row factor, and we test for the effect of the column factor. So we're going to look at 2 factors. If there's a factor between the rows and between the columns. So we need to look at the interactions between the row factor and the column factor. So look at this example. Pulse rates with 2 factors, the age bracket and the gender. So we have the row and we have the column. So the row has 1, 2, 3 rows, 3 brackets of rows, and your columns is separated by 2 columns, the female and the male. So in the table is shown of examples of pulse rates, beats per minute, categorized with 2 factors. One of the factor is the age bracket in years. So between 18 to 29, 30 to 49, and 15 to 80. This is one of the factors. And the second factor is the gender factor, female or male. So this tells us that we are going to be using the two-way ANOVA test. The first thing we have to look at is the interaction. The interaction between the two factors is the effect of one another. So if one factor changes for different categories than the other factor. So looking at one of the factors is the row versus the column, the row versus the column. So we're looking at the interaction. So we are going to be exploring the data. In the earlier table, we're going to calculate the mean for each cell and construct a graph. The individual cell means are shown in the table below. Those means vary from a low 64.8 to a high 82.2. So they vary considerably. So let's look at the first one, 80.4. So we looked at the sample mean of the first and of the second. So the mean of this data. So let's look at this data. Let's calculate the mean of 104, 82, 80, 78, 80, 84, 82, 66, 70, and 78. So if we would want to find the mean, let's remove this data. Let's clear this out. So let's input the data and then let's remove analysis. If we want to find the mean of a data, so I'm just going to go to Wolfram Alpha and I want to find the mean of, and then I'm going to input the data 104, 82, 80, 78, 80, 84, 82, 66, 70, and 78. And I'm going to close it. And I want to find the mean of that. The mean is 80.4, which is exactly what I was given. So I'm going to do the same with the male. And I'm going to have to do that all those 3 times. So this is the mean for the female between 18 and 29. Then I'm going to look at the mean of the second value. So I'm looking at the second row. So 66, 74. I'm looking at the data of females, 96, 86, 98, 88, 82, 72, 80, and 80. And I'm going to close that. And I'm going to find the mean to be 82.2. And that should match my table. So I'm looking over here at the means of each of them. So I found the mean of 80.4. I found the mean of 82.2. If I would go to the third one, 80.4, and then you would do the same for the males. So this just incorporates the sample means for X1 bar, X2 bar, X3, X4 bar. I'm looking at the sample means of each. So if we look at the interaction, an interaction effect suggests that they are parallel. So there's no interaction. If the line segments are approximately parallel, so right here, we're looking at the age gaps. Look at the differences between the means. So they are significantly different. There's no interaction. So there's not an appearance to be an interaction effect. So with the sample data categorized with 2 factors, a variable and a column, a row variable and a column variable, we will use a 2-way analysis of variance to conduct the following 3 tests. We are going to be testing for an effective interaction between the rows and the columns. We're going to test for an effect of a row column and an effect of a column factor. So there's 3 different tests. The way that we calculate it and the requirements used is the normality from each cell. Each of the sample values come from an approximately normal distribution. So we're going to look at each of them independently. So each of the rows here They must be normal. And they do. There's not an outlier. Each of the cells show normality. There's must be variation. So we look at the populations have the same variances, sigma squared. Sampling, the samples are coming from a sample, random sample, or a quantitative data. That is correct. We are going to check independence. The samples are independent of each other. There's a two-way. The sample variances are, or sorry, the sample values are categorized in two ways. Yes, in gender and in age. Those are my two categories. And I have to have a balanced design. All of the values have the same number of sample values. Yes, let's check how many sample values we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, they all have the same size of my cells. The balance design. All of the cells have 10, the same number of values. They each have 10 values. So the first thing is we're going to look at the interaction effect. Is in the two-way analysis of variance, we begin by testing the null hypotheses that there's no interaction between the two factors. We are going to be using technology to find the p-value corresponding to this test statistic. So here we are going to start using StatDisk to find the F test statistic and the p-value. So let's go ahead and do that now.